This is 9.1, and we are graphing quadratic functions. So we want to think about what that means. Quadratic, we may not have heard that word in a while. We may not remember what it means, but hopefully it jogs your memory. Quadratic just means degree 2. So if you notice, this is standard form for a quadratic function. Some number with x squared plus some number with x plus a constant. So what we've been used to seeing with factoring, but now it's just a function. What does that mean? I have my fancy function notation, f of x. All that it means is that we're looking at it on a graph, right? So we're now graphing these trinomials that we were factoring before. And don't worry, we're still going to be factoring them, which is why you need to remember how to factor. You need to know how to factor, right? And we all do. So before we go too far into what the problems are going to look like and what exactly you're going to be doing, we have to kind of get some vocab out of the way, unfortunately. So again, this is standard form for a quadratic function. The shape of a quadratic function is called a parabola. I think we've talked about that word in earlier chapters, right? That just means that U shape, right? Parabola is just that U shape that you get when you graph a quadratic function. The parabola is either going to open up or down. In this particular example, it's opening up, right? So this would be a parabola that's opening up. We're going to see that when that a value, that number in front of x squared, if it's a positive, then that's when we have this open up. So if a is positive, that's when it's going to open up. And if a is negative, that's when we'll see the parabola facing down. And we'll see it throughout our examples today. So a couple of things in terms of what we see on the graph. So we see our parabola as our U shape. And hopefully there's something else that sort of strikes your fancy. You have this dashed vertical line. So that dashed vertical line right there is called your axis of symmetry. And we are going to abbreviate that AOS for short. So your axis of symmetry, kind of self-explanatory, it cuts your parabola in half. So it's a vertical line that cuts down right smack in the middle of that parabola. It is a line of symmetry for your parabola. So it's a line of symmetry. It cuts the parabola in half. And the important thing to note with axis of symmetry is that when you write the axis of symmetry, it's always x equals a number. Students often forget that. They want to say the axis of symmetry is 2, and that's just not true. It's a vertical line. Take a look at it on the graph, right? It's a vertical line. So we need to write it like the equation of a vertical line. Remember, x looks like that half of v, v for vertical, x equals a number is a vertical line. So that's my axis of symmetry. The axis of symmetry cuts that parabola in half, and it always goes through this point right here, right at the base of that parabola if it's opening up. And that point is my vertex. So that point is my vertex. It always lies on the axis of symmetry. And it's either the highest or lowest point. It's always a min or a max. In this particular example, you can see it is the lowest point on the parabola. There are no points on the parabola below that vertex. So in this case, it would be a minimum. If my parabola opens down, then my vertex is going to be a max. And again, we'll see that in some of our examples as we move through. Some other key features of the parabola that are very similar to linear functions, so we should know all of this already, would be like this point right here. This point is where the parabola is intersecting the y-axis. So I'll give you a second to think about what that's called because everybody should know what that word is. That's my y-intercept. okay? My y-intercept, just like it always is, the point on the graph that intersects the y-axis, right? Where my parabola crosses the y-axis. So where parabola crosses y-axis. And if you recall from linear functions, the y-intercept, because it's on the y-axis, has a 0 value for x. So when you write that y-intercept, it's always 0, comma, a number. The other thing that you should recognize from linear functions would be your x-intercepts. The only strange thing is that you now have 2, most of the time. Sometimes we will still only have 1, and we'll look at some of those again as we move through our examples. Just like with linear functions, your x-intercept is where it crosses the x-axis. So where parabola crosses the x-axis. And just like with linear functions, because it's a point on the x-axis, it will always have a number for x and 0 for y. And so again, hopefully what's comforting that x and y intercept definitions are identical to any functions under the sun. Linear, quadratic, cubic, it doesn't matter. So those are standard definitions. So hopefully that feels like a refresher. The only thing that we want to take note of, something we're being sophisticated, we're increasing our vocabulary. Those x-intercepts are sometimes referred to as zeros, and the NJSLA loves that word for intercepts instead of zeros. So they could be called x-intercepts. Sometimes they're even just called intercepts, which is a little vague. Zeros is the preferred one, or roots. So you might also see the word roots as well, R-O-O-T-S. Any of those words, they all mean the same thing. They're just different ways of expressing the x-intercepts for the function. So those are your key features of the graph. Again, you have your standard form for a quadratic function. If that number in front of x squared is positive, you'll get a parabola, a U shape that is facing up, which will make my vertex, this point right here, the lowest point on my graph, a minimum value. The vertex is always lying on that axis of symmetry, which serves as a line of symmetry for the parabola. It cuts the parabola in half. I have my y-intercept and my x-intercepts that I know and love from linear functions. It's identical, where it crosses the y-axis, where the parabola crosses the x-axis. And then the only other thing that we might discuss, might come up through some of our problems, is this other point right here. This point is the mirror image of the y-intercept. So it's the y-intercept reflected across that axis of symmetry. So this we'll talk about is our symmetry point, reflection point. It's not super necessary in your understanding, but you're going to need to graph at least 3 points minimum, most of the time 5 if possible. So it's just nice, the more points you have, the more accurate your parabola will look. So we're going to incorporate that reflection point when we go to graph. Okay, so let's take a look at just, what some of this might mean, what it might look like. All we're going to do for today is just focus on identifying and then being given key pieces of information and then graphing them ourselves. We'll wait till tomorrow. We'll start to move into, here's a function, now find all this stuff. Today, we're going to give you all this stuff. So here's a picture for number 1. And like I said, for number 1, we're just identifying first key features. So all I want to do is, this graph is given to me. It looks like this. This is what it looks like. I didn't draw. I mean, I did draw, but you wouldn't be drawing it. The graph is being given to you. So if you go to take your 9-1 quiz, maybe there's a picture of a parabola that looks like this, and it asks for those key features. So does this parabola, my green parabola, does it open up or down? So you can see that my parabola opens up. My axis of symmetry, important. Remember, axis of symmetry is always x equals a number. So I think it's great. Get that written before you go and find that number. If you're searching for the number first, you might be inclined to just write the number itself on the line. Axis of symmetry is a vertical line. It has to be written as x equals a number. So let's take a look. I mean, this line is filled in for me. I'm just figuring out the equation of that line. It's x equals a number. Well, what x value is it hitting? It's going through that x equals 1 notch, right? So that's a vertical line at x equals 1. So what is my axis of symmetry? X equals 1. Now, what's really cool is you'll start to see the relationship between the axis of symmetry and your vertex. That vertex is always on the axis of symmetry. So let's think about what that means. The axis of symmetry says x equals 1, and I'm about to write a vertex point as an ordered pair. I'm trying to identify that ordered pair. So let me just grab those coordinates, right? 1, and then let me count. Negative 1, 2, 3, 4, 5, 6, 7, 8. So this point right here, this vertex point, is at 1, comma, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. If you notice, hopefully you see a little bit of a relationship between my axis of symmetry and my vertex point. That x value for my axis of symmetry, that x value for my vertex is my axis of symmetry number. They will always be the exact same number because my vertex is on my axis of symmetry. Makes perfect sense. Is that vertex a max or a min? Because the parabola opens up, there are no points below that vertex. There's nothing down here on my graph, so it is a minimum value. There's nothing below it. My y-intercept, where the graph crosses the y-axis. So I look on the y-axis, where does my parabola cross? And let me count. 1, 2, 3, 4, 5, negative 6, right? Am I just writing negative 6? No. My y-intercept is always 0 for x and some number for y. Now, this is what I was talking about before with that reflection point. So the reflection point is just the mirror image of that y-intercept. So again, I'm just pulling these coordinates off of my graph. What is this ordered pair, this coordinate? Okay, well, it's positive 2, negative 6. And you can start to see some relationships, although it's not super necessary. You can start to see some relationships between your reflection point, your y-intercept, and your axis of symmetry. That axis of symmetry value of x is right directly in between your y-intercept x value and your reflection point x value. Makes sense. These are mirror images of each other. They should be equally distanced from that axis of symmetry. Really cool. My x-intercepts, my zeros, because that's the word we're going to start to incorporate into our vocabulary. I have my x-intercepts. Well, where are they? That's where my graph, my parabola crosses the x-axis. So I'm pulling on these points. What do x-intercepts look like? It's going to be some number for x and then a 0 for y, because I'm somewhere on the x-axis, which means I don't have any up or down. I have no y value. So if I'm over here at this x-intercept, at this 0, I'm at 1, 2, 3, 0 is one of my x-intercepts. If I look at this x-intercept, what's the ordered pair on that guy? That's at negative 1, 0. That's my other x-intercept. All I did was pull these data pieces from that graph. And I'm making sure that how I'm writing things is appropriate. So my axis of symmetry should be a line. My vertex should be an ordered pair with a comma and parentheses. My y-intercept and x-intercept should be ordered pairs with commas and parentheses. My y-intercept should have a 0 for x. My x-intercepts should have zeros for y. All of that should fit.